After skimming past the Sun at a distance that should have torn a normal comet apart, 3I/Atlas was expected to fade into something familiar. It did not. On November 30th, 2025, the Hubble Space Telescope turned back toward the object long after the moment of danger had passed. What it captured was not a simple tail drifting away into space, but a vast, glowing structure shaped like a teardrop suspended around the object's core. Even more unsettling was its orientation. The narrow end of that glowing shape pointed straight toward the Sun, forming what scientists call an anti-tail, a rare feature that defies everyday intuition. This was the exact kind of behavior previously flagged by Avi Loeb, whose predictions about 3I/Atlas had already stirred debate. Some researchers saw confirmation, others urged restraint. NASA emphasized that standard comet physics could still explain what Hubble saw, pending further spectral data. So the question remains unresolved. If 3I/Atlas is just a normal comet, why does it keep doing things that do not seem normal at all? By the end of 2025, scientists were no longer debating one basic fact about 3I/Atlas. Its path through space had already settled that question. The object was moving on a hyperbolic trajectory, meaning it was not bound to the Sun and had never been part of the solar system. Like Oumuamua in 2017 and 2I/Borisov in 2019, 3I/Atlas was only passing through, a visitor from beyond our cosmic neighborhood. That classification alone placed it in a rare category. Only 2 interstellar objects had ever been confirmed before. Each one challenged expectations in different ways. Oumuamua showed no obvious comet tail. Borisov behaved more like a traditional comet, but still carried chemical signatures unlike anything seen before. When 3I/Atlas was added to that short list, astronomers knew they were once again dealing with something that did not come with a manual. As 3I/Atlas approached perihelion, its closest point to the Sun, expectations were fairly conservative. Comets are fragile by nature. When they pass close to the Sun, intense heat can crack their surfaces, trigger violent jets, or tear loosely bound material apart. In many cases, the structure becomes chaotic, and what remains is difficult to interpret. If 3I/Atlas followed that familiar pattern, the aftermath would likely be noisy, unstable, and scientifically frustrating. But that is not what happened. After perihelion passed, the object did not collapse into confusion. Instead, it remained coherent enough to be observed in detail. On November 30th, 2025, the Hubble Space Telescope turned back toward 3I/Atlas, now located roughly 178 million miles from Earth. At that distance, atmospheric distortion was no longer an issue. The observation was clean, direct, and free from the uncertainties that affect ground-based imaging. This timing made the data especially valuable. Post-perihelion images of interstellar objects are extremely rare, particularly when the object survives intact. Scientists were no longer guessing how 3I/Atlas might react to solar stress. They were seeing the result. From a research standpoint, this should have been the quiet phase. The most dangerous part of the journey was over. The Sun's influence was weakening. In theory, what remained should have been a stable, predictable object. Yet stability did not bring simplicity. Because at the exact moment when scientists expected clarity, Hubble revealed something that did not fit neatly into existing expectations. And that was when the story of 3I/Atlas began to take a far more unsettling turn. When scientists examined the new image captured by the Hubble Space Telescope, one detail stood out immediately. Surrounding the core of 3I/Atlas was a vast region of light, smooth and continuous, forming a shape that was unmistakable. It looked like a glowing teardrop suspended in space. No advanced terminology was needed to understand what made it strange. The image showed a bright, rounded region near the center, followed by a long, narrowing extension that tapered to a point. It was not messy. It was not scattered. It looked organized, almost deliberate, as if the light itself had been shaped rather than thrown outward at random. Based on measurements taken directly from the Hubble data, the scale of this structure was enormous. The rounded, luminous region measured roughly 25,000 miles across. Extending from it was a narrow feature stretching close to 37,000 miles in length. These were not subtle details visible only through heavy processing. They were dominant features of the image. What mattered just as much as size was definition. Typical comet tails appear thin, wispy, and uneven, shaped by solar wind and radiation pressure. They often fan outward, losing coherence as distance increases. The structure around 3I/Atlas did the opposite. Its edges were well defined. Its brightness was concentrated. Most importantly, it had a clear direction. This was not a cloud slowly dispersing into space. It was a form that held together. That distinction changed how the image was interpreted. A loose tail can be dismissed as debris reacting to sunlight. A compact, directional structure demands closer attention. It suggests that whatever was producing the glow was doing so in a controlled and consistent way, even after the object had already passed its closest encounter with the sun. For many observers, this raised an immediate red flag. Perihelion is when fragile objects are expected to break down. Heat stress peaks, surfaces fracture, jets fluctuate unpredictably. Yet here was 3I/Atlas, after that moment had passed, displaying a structure that looked stable rather than damaged. The teardrop shape was not just unusual, it was persistent. That persistence forced scientists to pause before reaching for easy explanations. If solar heating had created this structure, why did it remain so clean afterward? If it was simply leftover material, why did it not spread out or fade more rapidly? These were not rhetorical questions. They pointed directly to the heart of the mystery, because once the image was seen for what it was, a larger question followed naturally. What could possibly hold a structure this large, this defined, together after a close encounter with the sun that should have torn it apart? The strange shape seen in Hubble's image became even harder to ignore once scientists focused on its direction. Under normal circumstances, a comet's tail points away from the sun. Sunlight and solar wind push gas and dust outward, creating a long trail that follows a simple, familiar rule. But there is a rare exception to that rule, something known as an anti-tail. Instead of pointing away, an anti-tail appears to aim back toward the sun. It is not common, and when it does appear, it is usually faint, brief, or dependent on viewing angle. That is why the case of 3I/Atlas stood out. In the new image captured by the Hubble Space Telescope, the anti-tail was not subtle. It was bright, sharply defined, and stretched across tens of thousands of miles. More importantly, it was not a side detail. It formed the narrow, pointed end of the glowing teardrop shape itself. The entire structure seemed organized around it. Visually, the effect was unsettling. The sharp end of the luminous region pointed straight toward the sun, directly contradicting what most people expect when they think about comets. Instead of being pushed away, the structure appeared to lean inward, as if resisting the solar forces acting on it. This alone would have raised eyebrows, but the deeper concern came from how well the toggle anti-tail fit into the rest of the image. It was not detached or misaligned. It did not look like a separate feature layered on top of the glow. It aligned cleanly with the rounded luminous region, as if both were part of the same system. That alignment mattered. Anti-tails are often explained as geometric illusions, caused by how dust spreads along an object's orbit and how that orbit lines up with the observer's viewpoint. In those cases, the effect is usually fleeting. As the geometry changes, the anti-tail fades or shifts, but with 3I/Atlas, the structure appeared stable. The pointed end remained fixed in direction. The shape did not blur or fragment. Instead of looking like a temporary visual trick, it behaved like a persistent feature. That persistence is what pushed the discussion beyond casual explanation. If this were only a matter of perspective, scientists would expect the effect to weaken or distort as conditions changed. Yet the anti-tail remained tightly connected to the glowing structure, holding its form even after the object had passed its most intense encounter with the sun. At this stage, no one was claiming certainty. But the questions were becoming harder to dismiss. If the anti-tail of 3I/Atlas is simply a geometric effect, why does it appear so dominant, so well organized, and so stable? And if it is not just geometry, what exactly is keeping it that way? What unsettled researchers even more was not just what Hubble saw after perihelion, but how little that image differed from what came before. When scientists placed the post-perihelion image from November 2025 alongside earlier observations from July 2025, the comparison raised immediate concern. The overall shape remained strikingly similar. The glowing regions still formed the same teardrop outline. The narrow extension still pointed in the same direction. Even the relative scale of the structure showed no dramatic change. In other words, the object did not appear to be reacting. This was unexpected. Perihelion is not a gentle milestone for a comet. It is the most punishing phase of its journey. Solar radiation intensifies, surface temperatures spike, internal stresses build rapidly. For objects made of loosely bound ice and dust, this is often where cracks widen, jets shift unpredictably, or the nucleus begins to fragment. In some cases, comets simply do not survive at all. Yet 3I/Atlas emerged from that encounter looking almost unchanged. There was no sign of chaotic dispersal, no sudden asymmetry, no evidence that the structure had been violently reshaped by heat. Instead of appearing scarred or distorted, the glowing formation retained its coherence as if it had passed through perihelion without suffering the kind of damage scientists usually expect. That stability was troubling. In typical scenarios, even when a comet survives, its appearance evolves. Tails thin out, emission patterns shift. Bright regions expand or fade unevenly as material is lost. With 3I/Atlas, those familiar markers were largely absent. The structure did not look like something recovering from stress. It looked preserved. From a scientific standpoint, this narrowed the range of explanations. If extreme heating had driven the observed features, some change would be expected once the heat subsided. If the structure were fragile, it should have loosened or blurred over time. Neither outcome appeared in the data. Instead, the object seemed to maintain its form across months, spanning both sides of perihelion. This persistence suggested that whatever was shaping the glow around 3I/Atlas was not a fleeting reaction. It hinted at a mechanism that continued operating before and after the closest approach to the sun. That idea alone was enough to make many researchers pause. No conclusions were drawn at this stage. But assumptions were quietly reassessed, because when an interstellar object endures the harshest conditions of its journey and comes out looking almost the same, the question shifts. It is no longer about how it survived. It becomes about why it did not change. And that leads to a far more unsettling question. What could possibly allow a structure like this to hold its shape under conditions that should have torn it apart? One of the earliest alternative readings came from Avi Loeb, whose previous work on interstellar objects had already placed 3I/Atlas under closer examination. Rather than focusing on whether the object fit an existing category, Loeb concentrated on how its visible structure could physically form and remain stable. His proposal centered on mass. Instead of assuming the glowing teardrop was produced mainly by fine dust, Loeb suggested that it could be shaped by multiple large, solid fragments separating from the main body. These fragments would behave very differently from dust particles. Heavier and more cohesive, they would not spread out quickly or respond uniformly to solar radiation. Their combined motion could maintain a compact structure rather than a diffuse cloud. This idea carried an important implication. If the material around 3I/Atlas consisted of substantial fragments rather than lightweight debris, then gravity alone would not fully describe its motion. As gases escaped unevenly from these fragments, the object could experience a small but measurable non-gravitational acceleration, a subtle push that shifts its path without requiring any external force or unknown technology. Non-gravitational acceleration itself is not unusual. It has been documented in many comets and is typically linked to outgassing as ice heats and vaporizes. What made 3I/Atlas different in Loeb's view was how organized the resulting structure appeared. The glow did not look chaotic or short-lived. It appeared coherent, directional, and persistent. The most critical point in Loeb's argument involved geometry rather than speculation. Before the post-perihelion image was released, he had published models predicting where an anti-tail should appear if his interpretation was correct. When the Hubble image became available, the position of the anti-tail aligned closely with those predictions. To Loeb, this alignment mattered. It suggested that the structure followed a testable pattern rather than emerging randomly after the fact. That alignment did not end the debate. Many scientists cautioned that matching one geometric feature does not automatically validate an entire model. Complex systems can produce similar outcomes through different mechanisms, and coincidence cannot be ruled out without additional data. Loeb did not claim otherwise. He presented his interpretation as a hypothesis grounded in observable behavior, not as a definitive answer. The image, in his view, raised questions that deserved closer examination rather than immediate dismissal. Whether the explanation would hold depended on further measurements, especially those capable of identifying the composition and dynamics of the material involved. At this stage, the image itself had done its job. It had introduced a possibility that could not be ignored, but also could not yet be confirmed. And that left a deeper question hanging in the background. Is correctly anticipating the shape of a structure enough to change how 3I/Atlas is understood, or does it simply show how much remains unknown? While some interpretations pushed the discussion into unfamiliar territory, the official response from NASA remained measured and consistent with established comet science. From NASA's perspective, nothing observed so far requires a new category of object or an unconventional mechanism. The motion of 3I/Atlas, including the subtle deviations from a purely gravitational path, can still be explained using standard comet physics. In particular, non-gravitational acceleration is a known phenomenon. It has been observed repeatedly in comets when gas escapes unevenly from their surfaces, creating small but detectable changes in trajectory. In this framework, what appears unusual at first glance does not automatically imply something unknown. Outgassing can produce complex shapes, shifting brightness patterns, and even temporary structures that look organized when viewed at the right angle. Radiation pressure, solar wind, and the geometry of the orbit can combine in ways that are not always intuitive, especially when dealing with an object entering the solar system from a completely different stellar environment. NASA has also been clear about what the current data does not show. There is no direct evidence that 3I/Atlas is artificial in origin. There is no confirmed sign of an abnormal propulsion system or any force acting on the object that cannot be accounted for by known physical processes. The images alone, no matter how striking, do not provide enough information to determine composition, internal structure, or the precise mechanism shaping the observed glow. That limitation matters. Images reveal form, but not substance. They show where light is emitted, but not what is producing it. Without detailed spectral measurements, it is impossible to say which gases are present, how dense the material is, or how it is being released. From NASA's standpoint, drawing strong conclusions based solely on morphology would be premature. This cautious stance reflects a broader principle in planetary science. Extraordinary interpretations require equally strong evidence, and that evidence must come from multiple, independent measurements. Until those measurements exist, the safest explanation remains the simplest one that fits the data. As a result, NASA has emphasized that all conclusions about 3I/Atlas are provisional. The object has not been fully characterized, and key questions remain unanswered. Its behavior may ultimately prove to be unusual, but unusual does not mean unexplainable. For now, the disagreement is not about belief, but about thresholds. How much evidence is enough to move beyond standard models? How much uncertainty is acceptable before proposing alternatives? And that brings the discussion to a critical pause, because if images are not enough and motion alone cannot settle the issue, then the real answer must lie elsewhere. So the question becomes unavoidable. What kind of data would finally be enough to resolve this debate? With images alone reaching their limits, attention shifted to a different kind of evidence, one that does not rely on shape or appearance. The next phase of observation focuses on light itself. The Hubble Space Telescope is continuing its study of 3I/Atlas using ultraviolet spectroscopy, a method designed to break down the object's glow into distinct wavelengths. Unlike images which show structure, this technique reveals what is actually producing the light. The goal is straightforward in principle. Scientists want to identify the gases surrounding 3I/Atlas as it moves away from the Sun. If the object is behaving like a typical comet, ultraviolet data should reveal familiar signatures. Carbon monoxide, carbon dioxide, and water vapor are among the most common gases released when cometary ice heats up. Each of them leaves a recognizable fingerprint in ultraviolet light. Finding those signatures would not end the discussion, but it would anchor it. It would mean that the striking structure seen in the images is being driven by known materials responding to solar energy in expected ways. In that case, the unusual appearance of 3I/Atlas could be explained as an uncommon but natural outcome of standard processes acting on an interstellar body. But the more consequential outcome lies in the opposite result. If those familiar gases are weak, absent, or inconsistent with the brightness and shape of the glow, the interpretation changes. A lack of expected cometary signatures would force scientists to reconsider what is driving the observed emission. It would not immediately point to a new explanation, but it would remove the most comfortable one. That distinction is critical. Spectroscopy does not speculate. It either detects specific substances or it does not. Where images invite interpretation, spectral data sets boundaries. It tells researchers what cannot be responsible for what they are seeing. This is why ultraviolet measurements matter more than any single photograph. They have the potential to separate appearance from cause. They can confirm whether 3I/Atlas is releasing material in the same way other comets do, or whether something about its behavior falls outside established patterns. Until those results are in, every explanation remains provisional. The object may turn out to be an interstellar comet with unusual geometry and timing. Or it may reveal gaps in current models that require refinement. Either way, the The ultraviolet data represents the first step toward resolution, not escalation. For now, the mystery remains suspended between two possibilities. One leads back to familiar physics. The other opens questions that extend beyond shape and motion, and that leaves a final uncertainty hanging in the background. If the expected cometary signatures are not there, what explanation will scientists be forced to consider next? By the end of this observation window, a few facts are no longer in dispute. 3I/Atlas survived its closest encounter with the Sun. It emerged without obvious signs of collapse, fragmentation, or chaotic deformation. Instead, it revealed a stable, coherent structure marked by a glowing teardrop shape and an anti-tail pointing back toward the Sun, features rarely seen so clearly in an interstellar object. What remains unresolved is how to interpret those facts. For some researchers, the image suggests that familiar assumptions may need refinement. A structure this large and persistent challenges expectations about how fragile cometary material should behave after extreme heating. It invites questions about mass distribution, fragmentation, and the forces shaping material around objects that did not form in our solar system. For others, caution remains the guiding principle. Unusual does not mean inexplicable. Comets have surprised scientists before, and non-gravitational effects driven by outgassing are well documented. From this perspective, the image is striking but not yet decisive. Without knowing exactly what gases and materials are producing the glow, form alone cannot carry the weight of a conclusion. That is why the story is still unfolding. The Hubble Space Telescope continues to collect data, moving beyond images and into ultraviolet spectroscopy. Those measurements are expected to clarify whether 3I/Atlas is releasing familiar cometary gases or whether something about its behavior falls outside what current models comfortably explain. Until that information is available, any interpretation remains provisional. This is where science slows down by design, not to suppress ideas, but to test them. Right now, 3I/Atlas occupies an uneasy space between categories. It looks like a comet in some ways, and unlike one in others. It behaves predictably in motion, yet unexpectedly in form. Whether that tension leads to a deeper understanding of interstellar comets or forces scientists to confront gaps in their models depends entirely on what the next data reveals. So the question remains open. In your view, is the glowing teardrop around 3I/Atlas simply an unusual but natural feature of an interstellar comet? Or a reminder that we still do not fully understand what passes through our solar system? Share your thoughts in the comments and follow mindgap as we track what the next observations reveal.